Hey, everybody, welcome back. This is the third week of the Free Code Camp Oklahoma Advent of Code 2021 event. We're walking through the Advent of Code puzzles for the year 2021 and just trying to learn our way through this and hopefully get some exposure to some new software development and programming concepts along the way. Ultimately, this is just for fun and for learning. Again, my name's Floyd. I am the owner of a small software consultancy called Canyon Trail. I've been writing software professionally for about 20 years. I've also led companies, that sort of thing. Um, some of the other people that may be on stream with me include you. So if you really love one of the problems, had a lot of fun doing it, had a lot of pain and heartache going through it, and finally solving the problem, I'd love to have you on stream. Love to hear from you. If you're interested in that, hit me up on Slack and we'll figure it out. Um, Matthew Lee is going to be joining us again. His number of stars, I think, is outdated now because he's solved some more problems. This is actually from last week. Again, he's from Deep Fork Technology. He's pretty new to the software industry, but he's getting in there, getting it done. He's kicking some tail. So again, what to expect? We're going to talk about concepts and fundamentals. You're going to see some TypeScript code. You're going to see some Python code. I will admit I didn't get both TypeScript and Python done for for every single solution that we're going to be walking through. So we're going to kind of be mixing and matching a little bit. I tried to give somewhat equal attention to both languages. You're going to see unit tests. You're going to see code on GitHub. There's discussion available on Techlahoma Slack. You're not going to see a whole lot of live coding. You're not going to see perfection. You're not going to hear perfection. We're also not going to say this is the one true answer because that just doesn't exist, even in something that's as well defined as Advent of Code. Also, you're not going to see timely solutions, both in me getting them done and posted up to GitHub, as well as we're quite a bit behind where today's puzzles are. So if you remember from last week, we only got through till about day 5. So we're going to start with day 6, which I know a lot of people had some struggles with. I don't expect we're going to get farther than about day 10 or day 11 today, but we'll see. Excuse me, I'm allergic to Oklahoma. All this pollen, blah. If you're playing around with Advent of Code, if you're participating, don't feel like you're alone in it. Don't feel like you've just got to figure it out all by yourself. The Techlahoma Slack organization is here if you want some hints, if you want to talk about the solutions, if you're just trying to figure out a strategy or something, there's plenty of places for you to get plugged in. There is a template repository if you're just brand new to this particular event. So you can download the template repository and it'll give you a little bit of a head start putting together TypeScript and or Python unit tests, which can be really, really valuable for solving these problems. The solutions repository also available on GitHub. Feel free to fork it. This will let you play around with the solutions that have been posted. So there's my code there. There's some of Matt's code there as well. Is it Matt or Matthew? I keep asking.
Either way is fine.
All right. So I will probably do both just to keep it nice and confusing.
Perfect.
I'm going to say this every single time. Advent of Code is hard. So don't feel bad if you're not getting very far. Don't feel bad if like, wow, I have no idea what to do. Please plug into the community. Please ask for help. If you're just like, you know what, this is beyond me. I'm going to tap out at day 3. I'm going to tap out at day 8, whatever. That's totally fine. I'd still love for you to continue watching. Hopefully you'll still pick up something. Hopefully you'll still enjoy it and learn and become a better software developer. So before we get into day 6, I want to take a pause here and wax philosophical about. No, let me back that up. I want to kind of wax philosophical for just a minute about why I do Advent of Code, and hopefully this will encourage you to spend a little bit of effort on it as well, and help you feel like, okay, this is something that's worth doing. Obviously, the problems in Advent of Code are not, quote unquote, normal programming. This isn't anything that's even remotely similar to what most programmers do in their day-to-day jobs. So why should we do this? And does it really actually help us as software developers? And the metaphor that I'll give you is that a professional athlete, a basketball player, a football player, a swimmer, whatever, just go and scrimmage all the time, meaning they don't play the game over and over and over again. You'll see them do drills that focus on one particular activity, one particular skill, one particular movement, one particular kind of problem solving. And these drills help to really reinforce and create skills that may be hard to do in the game, so to speak. And for us as athletes of the mind, um, finding ways to do drills can be really, really helpful and make us more effective programmers. So for me, Advent of Code is really useful, one, because it helps me level up my skills in turning English into working code. Um, this is one of those things that no matter what kind of programming you're doing, eventually you're going to have to communicate with somebody, and somebody's going to have to communicate with you, and you're going to have to turn that squishy, ambiguous, hard to understand, very human communication into stuff that the computer understands: ones and zeros, trues and false, on and off, yes or no. Advent of Code really helps you reinforce that reflex and do it quickly, because like there's sort of a time aspect involved. Okay, there's going to be a next puzzle tomorrow, and I want to try to get it done today so that I can move on to the next one tomorrow. And so it helps to sort of build that skill of, I've got to get to the core of what's the problem to solve and how do I teach the computer how to solve it. One of the other things that Advent of Code really does for me is it helps me be humble about how much stuff I can fit into my head. Um, you'll hear me talk about test-driven development a lot. If ever you've met me and I haven't talked about test-driven development, it's weird. Okay, if you don't hear me talk about test-driven development, like, wrong with Floyd? Is he okay? Um, because test-driven development is such an important element of what professional software developers really should be doing. And Advent of Code is a great example for this. So for instance, when I approach one of the Advent of Code problems, the first thing I do is I grab the sample input that they give me, drop it into a test, and I run that sample input against my code and see if I get the output that it says that I'm supposed to get. Generally, I get a 0 because I just put placeholders in, and then I try. I'm gonna write some code and see if I can just solve this in one step. Usually, and especially now that we're up to day 14, day 15, day 16, usually the answer to that this late in Advent of Code is no, I can't do it in one step. So what you'll see is a bunch more unit tests than just part one, part two in the code that I'm going to show you. And the reason why is you're actually seeing my problem solving approach. You're seeing, where did I struggle? Where did Floyd struggle? Excuse me. Blah, allergies. Blah. Um, this idea, what I call problem solving humility. There's an idea that we've got to get out of our heads as software developers, that the best software developers are the ones whose brains are the awesomest. We can fit the most information or the most ideas or the most concepts in our head. Um, this is just a really bad way to go about it, because most of the kinds of stuff that software developers will try and fail to keep in their heads is like, how does this algorithm work? What's the state of a virtual machine or something like that in a particular step of a computation? And if we're trying to juggle a bunch of information in our heads, we're usually going to be really bad at it. And being bad at it usually shakes out in bugs in our code. Now, if instead we're humble enough to say, there are some limits to this wrinkled wad of protein that we've got between our ears, and those limits make it hard for me to juggle information in my head. Instead, I'm going to make the computer remember that information. I'm going to break down the problems into smaller pieces, smaller steps, so that the computer can do this stuff instead of me having to sort of manage it and wrangle it in my head. This Advent of Code thing really helps with that, because it's easy to sort of, get some hubris going and be like, oh yeah, I can totally figure that out. I can fit every single detail and every single edge case into my head, and I can just sling out a, triply nested loop, and that'll make it. And then it doesn't work so well. So it's okay to be humble. It's okay to say, okay, I probably can't solve this in one step. I probably can't solve this in two steps. So let's break this down and let's figure out how can we turn this bigger problem into a smaller problem that I can unit test, maybe even an even smaller problem that I can then unit test. And in that too, this also helps to sort of refine that test-driven development discipline. red, green, refactor. Start with a failing test, write just enough code to make it pass, and then refactor as needed. A lot of times that refactoring comes at that step 2, right? Like step 2 is when you get the turn, like, okay, I got step 1 working, boom, it's done. And then step 2 shows up and it's like, well, crap, now I've got to throw all of this stuff away. Dang it. And this brings me to another point about what value I'm getting out of advent of code. And hopefully this is value that you're going to be getting out of it as well. Refining that discipline of writing readable, understandable, easy to change code. Remember that code is, yeah, the computer executes it, but really it's for humans. It's for us to read. And the computer executing it is really just kind of a byproduct. And going from that transition to here's the step 1 of a particular problem to here's the step 2 of that problem, it really simplifies that process if you've taken the time and spent the effort making your step 1 solution readable, understandable, and easy to change. All right. So all that to be said, hopefully that helps you get some understanding as to like, why should I even bother with advent of code? So now let us go and look at some code. All right. So we're going to talk about day 6. And I know day 6 was a real challenge for a lot of folks. So this was all about lanternfish. Lanternfish replicate every 6 days, but but brand new lanternfish take 8 days to replicate. Now, Matthew's on stream with us, and we're gonna go look at Matthew's code here in just a little bit because like he had a really clever solution that I really liked, and I wanted to give him a chance to talk about it. But at the end of the day, what a lot of people had happen is their part 1 solution worked fine, and then they just said, okay, well, how big is the population of lanternfish after a much bigger period of time? And you just wait and wait and wait, and your computer says, no answer yet. You're just going to have to keep waiting. So this is a performance problem, right? And performance problems usually are an issue of your algorithm takes up too much memory or it takes up too much CPU time. And in this case, it's both, because the instructions really sort of lead you down this path of modeling each individual fish as its own separate little thing. So here's the key concept in being able to solve day 6 well. If you have 2 different fish and their counters are both the same, let's say their counters are both 5, there's no difference between the 2 of them. So instead of modeling each individual fish separately, keep a count of how many fish are at a particular state with their counter at some numeric value. If you do that, then going from day 0 to day 1 to day 2 to day 3, so on and so on, just means shuffling around the counts a little bit. And let me show you the code that does that. Kimberly, font size check.
Okay, that looks good.
Awesome, thank you. So here's the code right here that does exactly that. Our population is an object where the keys are the counters and the values are how many fish there are. So at each step, we take whatever fish were at population 0. These are the fish that generate new fish. And we add those in to day 6. Why? Because their counters go from 0 back up to day 6, and then they spawn the same number of fish. So our new fish count is however many fish there are at counter 0. So this is really the magic here. So we can run this code right here over and over and over and over and over again. And it's never going to take up more memory, because really we're not taking up more space in memory. We're just making numbers bigger. Now, one of the interesting things that I did here is that this is a TypeScript generator function. So you see the star here. This is actually an infinite generator. So we can use this for 3 days, 6 days, 174 days, we can just keep consuming values from this generator function. So let's look at what that means. So here, population size at day. So we have our sequence. We do next because this is how sequence or generators in JavaScript work. And then we just go through in a loop, grab the value for whatever we need, and then as soon as the loop's over, we just return that value. So part 1, we get the population size at day 80. Part 2, population size at day 256. Now, this really, it's a trick, so to speak, because instead of modeling every individual fish, you're going to model counts. And this isn't really common in this kind of solution is not really common in typical programming. But it is important to recognize the difference between these are unique things that need to be unique versus these are all things that are identical. Now, next up, let's take a look at Matthew's code. Where? Aha. Okay. So your code was in a branch called, where was your code?
Is it Matthew? Day 6 was the branch. I don't know if it's in.
Oh, it's not in this repository. Is it in your repository?
I created a pull request for it. I don't know if it's like in main or.
Oh, okay.
What?
Aha. We found it. All right, so let's embiggen this a little bit. Now, where was the secret sauce here? So one of the cool things I love about this is these constants right here. I think this is really clever because instead of having magic numbers, these numbers mean things. I didn't do a great job of not having magic numbers in my code, but you definitely did, and this looks really nice. So, here we go. Here's the code. Here's the code right here. So, Matthew, okay, font size check real quick, by the way.
It's a little blurry, at least for me.
Better?
I think that looks good. Yeah.
Okay. So here's the magic code right here. I saw that and I was like, oh man, I want you to talk on stream about this. So break this down for us. Help us understand what's going on here.
Yeah. So I guess just starting from the beginning, whenever I first saw the problem, I was like, well, a for loop obviously isn't going to work for this. So I grouped everything into small chunks and created an array the size of basically our maximum days, which is however long the reset period between spawning is, and the extra I called it like first spawn penalty or something like that.
Yeah. So let's go back and look at that. First cycle penalty. Okay.
Yep.
Cool. So your total cycle. So this is your array length right here, which is that cycle length 6 plus your first cycle. Okay.
Mm-hmm.
Very cool. All right.
And so I put it into an array of that length, and then I realized that whenever you cycle through it, essentially what you're doing is you're taking each group of fish and you're pushing it one forward in that array, and then taking the front one, placing it into the 6th position, and then with that count that you just placed there, you're adding that to the 8th position in the array.
Yeah, that's really cool. So in effect, what you've got is sort of like this circular system here, where you've got an array. You take an element off the back, you put it on the front, and then you add it back into the middle as well, and then it just shifts over, and then shifts over, and then shifts over, and so it's just sort of this circular thing, kind of a circular buffer thing, and that's really, really clever. I like how this works. I feel like it's got some simplicity to it, but it's also very efficient. So this is really neat. Now talk to me about your testing process for this. So I see that you've got a test just for this cycle method, and I think this was just sort of validating. Did I get this part right?
Mm-hmm. Yeah, I mean, I'm still really new to TDD, so I'm trying to figure it out. But whenever I was writing this, I was like, okay, well, I want to cycle through it, so I need to make sure that I have this array which I think is the test input. And whenever I move it forward, I know that I want it to be like actually moved forward. And since that's the biggest part of it, I tested it to make sure that whenever I do cycle it, it turns out how I need it to be.
Awesome. Cool. Well, I definitely dig your solution, and I feel like the simplicity of it is really really elegant. I feel like mine is a little more crude in that respect, because it's all about like keys and value mapping. This matches up with that, and even though it works, I feel like the simplicity of this is just really charming. So I love that. Thank you for sharing that.
Mhm.
So let's talk about day 7. So day 7 was this thing with crabs. Let's go look at day 7. So we get basically it's a one-dimensional mapping of here are where a bunch of crabs in submarines are, because crabs in submarines are apparently a thing. And we have to figure out what is the right position in part 1 for all of them to have a minimum amount of distance, and we call that, for part 1, the distance is how much fuel are they going to consume to all go to that very same distance. Part 2 is a little more tricky. So part 1, you can definitely brute force it. Part 1 also, the solution for it mathematically is the median. I discovered that sort of by accident, because I walked into this problem thinking, okay, there's a tricky math hack for this. And median worked great for part 1. I could not figure out a tricky math hack for part 2. So let's talk about part 2 a little bit, because this is another problem where performance could become an issue. If I remember correctly, I had 100 crabs in my actual input. So for 100 crabs, it's not too bad to just compute differences. But for part 2, the distance from whatever your point was that you said was the answer, the fuel consumed for the crab gets bigger as it gets farther away exponentially. So instead of it being, so if the crab is 5 units away, instead of the fuel being 5, it's 5 plus 4 plus 3 plus 2 plus 1. Now, that form of 5 plus 4 plus 3 plus 2 plus 1, this is something called the sum of natural numbers up to n, and n in our case is 5. So this is something that you may or may not have encountered in a math class somewhere, but there's a way to do that without having to loop over each individual number. And that is this formula right here. So if we take, say, for instance, the number 3, 3 times 3 plus 1. So 3 times 3 plus 1 is 3 times 4, which is 12, divided by 2 is 6. So 1 plus 2 plus 3 is 6. This formula also gives us 6. And you can experiment with this however much you like. I remember, discrete mathematics in college, we actually had to go through the proof of this formula, but suffice it to say, this formula works. And this is the secret sauce to being able to do your day 7 part 2 without it taking forever. So let's look at the code for that. So let's see, here we are, part 1. So like I said earlier, the median is really the magic spot there. Whereas for part 2, this was really about figuring out what's the fuel at each potential location, and then figuring out what's the least amount of fuel. So really, I just took a brute force approach with this. But the nice part about that is, in this compute fuel function here, we're using that sum of natural numbers formula. So whatever the delta is, then delta here just being the distance from where the crab is to what our target position is, delta times delta plus 1 over 2, which is, again, that formula. So this is really the key to solving day 7 reasonably well. And if you know this, you can just sort of brute force it and it'll work. So let's talk about day 8. Now, day 8 was I would say pretty gnarly.
Floyd, really quick, just on that last solution, I wanted to point out that since you're looking for the median, I basically brute forced it in like the opposite way and found the median at each position and then did like a ternary search to find out what the lowest median would be. And I don't know if that's exactly what yours does, but
sounds like for part 1 or for part 2?
For part 2.
Okay. Now, there was some discussion on the Slack channel. Apparently, and I don't know if this just happens to be the way it worked out or if mathematically this is true, but there were some people that did some I forget the term for it, linear regression, I think maybe. So if I say, okay, I think the value is here, and then I'm going to test the neighbor value. Okay, that one's lower, so I'm going to keep going and keep going and keep going until it starts going the other direction. And I know this one has to be the lowest one, and so I return that one. And there were a handful of people that did that, and they talked about it in Slack, and they were successful with that. So I assume that means there's only one sort of minimum value, and that we don't have sort of like, okay, here's a one that's not the bottom, but it kind of goes down and then back up and then goes back down. So I assume there's some sort of like functional equivalent that only has one minimum, basically. All right. So day 8. So let's look at day 8 here. So day 8, this one was really fun. The 7-segment display. So we have to figure out, given a few pieces of data, what's the mapping between these letters and these letters here that operate a 7-segment display. There was a lot of discussion in Slack about this, and this was interesting because there were so many different ways to attack the problem. Like I remember one person said, the only things that you care about for the digit 4 are the what's labeled here is B and D, if I remember correctly. I'm honestly not completely sure about it, but at the end of the day, what we're trying to figure out is a mapping between one set of 7 letters and another set of 7 letters, given some data that's assumed to be valid. So part 1, if you remember, we know certain things. So if there are only 3 segments lit up, we know that there's only one digit that has 3 segments lit up, and so that's got to be 7. So we can just go by however many numbers of segments are lit up. But then part 2 is where we actually have to figure out the mapping. I went with the approach of doing permutations. So what is a permutation? A permutation is where you have a set of letters or a set of numbers, a set of symbols, and you have to figure out how many different ways can I arrange this set of symbols. Wait, no, day 8. All right. Now, a few different things that I also did with this is I went with numbers here. So I relabeled the segments with numbers instead of letters, just to simplify things a little bit for me. One of the other interesting things that I did, hopefully this is useful, is I did this segment patterns thing. So the digit 0 has segments 0, 1, 2, 4, 5, and 6 lit up. So 0, here, let me do this with the keyboard. So 0, 1, 2, so those first 3 segments lit up. Segment 3 is not lit up, but then segments 4, 5, and 6 are lit up. So 1 just has 2 and 5 lit up. So, and remember, we're doing 0-based indexing. So 0, 1, 2. So 2 is lit up. 3, 4, 5. So 5 is lit up for the digit 1. So on, so on. So we've got these patterns. So we know if I assume this is a 5, does it light up these particular segments? Then I inverted them. So you can use this invert thing. So it takes the keys and makes them values, and takes the values and makes them keys. So what this will do is it will tell me if I have a particular mapping, I look for a number in this numbers by pattern. It tells me whether or not that mapping is valid. So here's my permutation function. This is something that a lot of libraries have built into them. I wrote it pretty quickly because honestly, I didn't want to go try to hunt down another NPM library to install or do something like that. But really, you're just dealing with a set. You take one element out of the set, and then you permute that next set until your set is empty. So this is just going to give us every single possible combination of the letters A through G. If you also notice, I've got these types here. So I've got a wire position. So this wire position corresponds to these numbers up here. And then the wire, this corresponds to our input from the puzzle. And then our wire mapping says, given this letter, what position does it go with? So this wire mapping is really the thing that we've got to figure out in order to figure out part 2. Now, let's go have a look here. So this is parsing. Parsing is fun. Let me refresh my memory, and maybe it might be helpful if I... Okay. Here's my sample input. Again, the first thing I do when I go to solve any of these problems is I put my sample input here, and I do a day X part 1 sample input. And I do this assertion, and then I go write enough code to see if I can get this in one step or if I need to break it down. Here's some simple tests on a permutation. So, for instance, here's a permutation of A, B, and C. So here are all the different kinds of combinations of the letters A, B, and C in different orders. So in this particular case, one of the things that I also did is I did some tests on one particular bit of that sample input to try to figure out, can I find the mapping for this sample input? So I expect this mapping because this is one of the things that it broke down for us in the explanation. That mapping should be this. So the letter D maps to that segment 0. And again, that 0 is this top segment right here. So on, so on. Then we've also got another thing that is this matches mapping function. So I've got a mapping. And then I've got these samples here. And what I want to make sure is that for each of these samples, let's see, match mapping for S. Lit mapping to be true. So for each of these samples, I think 1, 2, 3, 4, 5, 6, 7, 8, 0. So all of the numbers are present here. Every one of the different numbers are present here, and I'm checking to make sure that each of them matches up. So I don't necessarily care what number it is. I just want to know if it matches. So with these two functions, I was able to put this together so that we get our entries. And so our entries are, we've got the things on the left side. These are the examples that we use to figure out the mapping. And then the things on the right side, those are the numbers we've got to do some math with. So step 1 is we've got to find the mapping. So given our samples, and I'm calling the left side the samples. So for our input up here, here's an entry. I'm calling this left side our samples. So given these samples, I've got to figure out the mapping. Then once I've got the mapping, I've got to figure out what are the digits on the right-hand side. And then I've got to add up those digits. So let's talk about how this find mapping function works. So you remember I talked to you about this permute function. So that I'm doing a permutation. I'm walking through every possible combination of wire to wire position mapping. And then I'm walking through each sample and I'm saying, does this match the mapping? Could this possibly be valid? So what that means is, for instance, if I've got a sample that's got 3 segments lit up, if those segments don't exactly match up to 0, 2, and 5, we know it doesn't match the mapping because there's only one digit that has only 3 segments lit up, and that's 7. So if we've got 3 segments lit up, but it's not 0, 2, and 5, we know that the mapping is invalid, and we can throw it out. So where do we go? So for each of these, we ask for each of the samples, does it match? If not, we bail out and we go to the next permutation. Now, this is still pretty computationally intense. It takes a while. It takes about 4 seconds for mine to run on my system. Not horrible, but there's also a little bit of optimization that I did with that. So the first one is this. So if we've got all 7 segments lit up, that's an 8, and we know that. So every 8 will always match every possible mapping because there's it's got light up all the segments, and there's no possible way for that to be wrong. And then the next thing is that I'm sorting the remaining samples by length. So that means we're gonna try 1 first, and if that works, then we're gonna try 7 because it's got 3 segments lit up. And if that works, we're going to continue trying bigger ones and bigger ones and bigger ones. And between these 2 optimizations, I was able to shave off about 20% of the time. So it went from 5.5 seconds to right at 4 seconds. But at any rate, the key here is just doing the permutation and just checking, and it works. So let's talk about day 9. I know Alex and I were talking prior to going live about day 9. So day 9 was all about, you've got a map of depths, and we've got to find the low points. So part 1 was all about the low points, and the low points are lower than any adjacent location. So we've got to figure out what are our adjacent locations. And one of the complicating factors of that is we might have a low point that's at the edge of the grid. So what do we do about that? There's a neat little trick. Yuri in Techlahoma Slack actually taught me this one a year or maybe 2 ago, and I'll show you what the trick is. This one is actually pretty awesome. Pad your grid. So if we take our grid values from the input and we put 9s all the way around them, then we don't have to care about boundary conditions. So if you loop starting at 1 and going to your grid size -2, then you don't have to worry about having low points on the edges and that having to be handled differently. So let me show you how that looks. So find low points. So our neighbor values for any given X value and Y value, we go left, X -1, we go right, X +1, we go up, X or Y -1, we go down, Y +1. So we can just loop through these neighbors and see if any of them have a value that is less than the one that we're at now. If they do, then it's not a low point. If there aren't any that have a lower value than the one we're at now, then we found a low point. So that's pretty simple for part 1. We just loop through all of the coordinates and look for anywhere that a neighbor is where no neighbor is lower. And the nice part about this is because we've padded our grid, we've put 9s all the way around. Actually, I put 10s if I remember correctly. Yeah, I'll show you here. Create grid. Where's create grid? Yeah. So I have a pad row. So what I did here is I just filled it with 10s, and then all of my inner rows I put a 10 at the beginning, 10 at the end, and then splatted the original values in the middle. So I've got my pad row at the beginning. I'm transforming each individual row in the middle, and then I've got a pad row at the end. So I'm surrounding my grid with 10s instead of 9s, but still works because they're still numbers. Now for part 2 of day 9, this is a great example of how to do a flood fill algorithm. So what's a flood fill algorithm? So if you use the bucket tool in an image editing program and you click somewhere inside of an image, it's going to flood fill that area of the image until it hits something that's a different color. This is the exact same algorithm that we're using here. Now, image processing tools, Photoshop, Paint.net, whatever, their flood fills are going to be a whole heck of a lot more optimized than what I've got here, because we're dealing with, tens of thousands of pixels in some cases, whereas here we're just dealing with, a few hundred, a few thousand, not a big deal. So let's talk about what is a flood fill algorithm. How does a flood fill algorithm work? In this particular case, we just care about what coordinates belong to what they call a basin. So what's a basin? It's anything that's surrounded completely by 9s. So if we do a flood fill algorithm, we stop when we hit something that's 9, and in my case, 9 or greater, because I padded with 10s. Still works. So how does that work? So we have a start point, we have our grid, and then we have our marks, which is a set. So a set just basically keeps track of unique things. So here's our start point, our value at our start point. We check and see, is it greater than 8? If so, we've hit a boundary and we just need to stop. If not, so if we've already checked it, we also bail out. Otherwise, we say, okay, we're going to fill this area. So we're going to mark this area. And then we're going to flood fill all of its neighbors. We're going to go up, we're going to go down, we're going to go left, we're going to go right, and we're going to flood fill all of those. So if you notice, we're calling flood inside of flood. What does that mean? It's recursive. In this particular case, this worked fine for me. Recursive algorithms don't always work great in this particular kind of case. I promise you, a recursive algorithm, if you were to use this to flood fill, say like a JPEG that's like 3,000 pixels wide by 3,000 pixels tall, this is going to go kaboom really fast. But for smaller input like what we're dealing with here, works totally fine. So the flood fill algorithm here is really the key to part 2, or at least my key to part 2. All right, now day 10. Okay, I'm going to get real vulnerable with you here about day 10, because I had an epic fail in my first attempt on day 10. So day 10 was all about parsing this gobbledygook and making sure that the braces were matched properly. Now, here's the way that I tried to go about this. I grabbed a parser library and I'm like, okay, I'll just use a parser library to do all the hard work. And that was an absolute epic fail. And part of the reason why is because I needed to find the exact position that the parsing broke down. And that's usually the hard part about writing parsers or using parser libraries, if you're trying to deal with failure cases. And this is all about the failure cases. It's not about telling you, yes, it's valid, no, it's not. It's about just exactly what kind of invalid is this. And trying the parser library just did not work well for me. So I probably wasted a fair bit of an hour going down that path, and it just went just bad, just wrong. Before I get too far into it, Kimberly, I'm going to pause and ask about what's going on in the Twitch chat. I know I've just been sort of rambling on for, 45 minutes now.
Yeah, not a lot has been said. I think people are following along though, and yeah, definitely post your questions or comments there in the chat.
Okay, cool. So here is what I went with for the solution to this. Let's go look at Floyd's day 10. Day 10. All right. So I made some little mappings just to make it easier to go find things, rather than having to sort of do if this, then that. So these little mappings here worked out really, really well. Then what I did, the part 1 map get illegal char. So what does get illegal char do? Illegal char pause. So what does it do? It calls run parsing. So what does run parsing do? Okay. We use a stack. So what's a stack? A stack is a data structure. In this case, we're backing our stack with an array, but a stack is a last in, first out data structure. LIFO, L-I-F-O, last in, first out. So if you push a value into a stack, and then you push another one, and then you push another one. So you push 1, 2, 3, 4, 5 into a stack, and then you pop, you get 5 back because it was the last one you put in. So the last in is the first one back out. So we use a stack to keep track of the nesting. So when you push, say, an open paren onto a stack, and then let's say we push a square bracket onto the stack. So left paren, left square bracket. Then we expect to see a right square bracket. And then if we see a right square bracket, if the thing that's at the top of the stack is a left square bracket, we know they match. We're good to go. We can pop that back off the stack. Then the next character, if it's a right paren, it matches with the left paren that's now at the top of the stack. That works. So a stack does really well at sort of matching nested stuff because it'll keep track of where you're at. So we're just walking through a position at a time, and then we're checking to see. So here's our current character. So open to close. What is open to close? It tells me, given this current character, so given my current character, so if I hand it a so basically this is just what am I doing here? Let's go look at my tests because honestly, I'm not sure what the heck happened there.
Are you checking for a null value or?
That seems to be what I'm doing. So here's a great example. One of the things I did is I made a bunch of test cases here, and I'm just looping through each of those test cases to make sure that I'm getting the expected value that I should. It works. So basically, yeah, this is just checking to make sure, is this a valid character? Oh, no. Do you know what this is doing? This is checking to see if it's an open bracket or open paren. If it's the thing that's supposed to be on the left-hand side. So if it's the thing that's supposed to be on the left-hand side, I'm pushing it into the stack. Otherwise, it's got to be something that's supposed to be on the right-hand side. So whatever's at the top of the stack should be the left side of whatever the right side is, right? So if open to close for the stack top doesn't equal my current character, then that means we're broken. We've got an invalid character, and we've got an invalid character at this position. And if they do match, we're just going to get rid of the thing that's at the top of the stack and move on to the next position. So this is, if it's a left brace, left bracket, left square angle bracket, whatever, if it's a left side thing, push it onto the stack. Otherwise, see if the nesting matches up. And if not, tell us where it broke. Now, that's great for part one, but part two, this part is really neat. So part two was saying what series of characters do we need to put to make all of the nesting work right? So what that means is at the end of a string, if we get to the end of the string and there's still stuff left in the stack, these are the things that still need to be matched. So what we're doing is, so we have a stack that's non-empty at the end of the string. So we just walk through and we get this completion score for whatever right side thing matches whatever left side thing is still left in the stack. So if we've got 2 left parens still left in the stack, we want to turn those into right parens. Then we want to get the score for them. And then, of course, we have to multiply each previous thing by 5 based on the rules of day 10. All right. So that's day 10.
Yeah, Eric said that he used the same basic technique, but he did it the hard manual way because he didn't know that there was a stack structure in JavaScript, and that he's learning a bunch through doing this.
Yeah, and what I very much could have made like a stack class that just sort of hides the fact that there's an array underneath. But the neat part about JavaScript is you can push stuff to the beginning of an array, or the end of an array, or in the middle of an array. Arrays are very squishy in JavaScript and TypeScript. Anything more from the Twitch chat?
No, but Eric did post a link to his solution. So
Cool. Good deal.
Share that.
All right, let's look at day 11. So day 11, this one was fun. And this is, we get to go play with some Python now. I realized at day 10, I'm like, I've been doing everything in TypeScript. I need to give some love to the Python folks. So day 11 was all about octopus, octopi, octopod, octopoxin. What's the right plural form of that? Octopuses. There we go. Sure. In a grid, and every so often they flash, and when they flash, they give energy to their neighbors, and those neighbors might flash, and they might give energy to other neighbors, and they might flash. And so we get this sort of interesting ripple effect with flashes, where one flash might trigger a whole lot of flashes. So the key element here, at least for my solution, was, well, number one, we can't use the same trick that we used for day 9, padding the grid. That won't help us here. So we've got to deal with the boundary conditions. We've got to deal with, am I at an edge or not? Oh well. The interesting thing about this was that you have to keep track of which octopuses, octopoxin, which ones have already flashed for the given step. Because they can't flash multiple times, and we got to keep a count of how many of them flashed. So what we don't want to do is this one flashes and it causes its neighbor to flash, and then we go back to this one, and it quote unquote flashes again. What we don't want is sort of an infinite loop of flashes cause more flashes, because they shouldn't do that. So that's why we have to keep track of which octopods have already flashed. Notice I didn't use the word octopus in here anywhere, because apparently I struggle with plural forms of Latin words. So let's look at this. So here's this try flash. So given a coordinate, here's our grid, and a set of flash locations, we're going to try to see if this octopus needs to flash. So we get our value out of the grid, and if the value is less than or equal to 9, we don't need to do anything. Now, if the coordinate is already in the flash locations, that means it's already flashed, so we should not go farther. Then we add the location to the flash locations. Okay, this octopus just flashed. And then we've got a list of candidate neighbors. So we have to check even diagonal neighbors. So instead of there being 4 neighbors, now there are 8 neighbors. So I did east, northeast, north, northwest, west, southwest, south, southeast. And I did this on purpose because it made it a whole lot easier for me to make sure, did I get all of them right? Because I could just sort of walk around the compass and make sure that I got all of them. And then neighbors, I'm filtering based on this valid coord function, which is just making sure that my boundary conditions are okay. So I've got my candidate neighbors, and I'm just filtering out the ones that are beyond the bounds of our grid. So given all of these neighbors, the first thing I do is I increment all the neighbors, because when you flash, you're supposed to increment all the neighbors. And then I'm gonna go to that coord, and I'm gonna go try to flash that one, and so on and so on. So if you notice again, Try flash eventually calls try flash. This is recursive. This worked fine for me. I didn't have any trouble with it. And also part of the reason why I wasn't too worried about this being a problem is because it's a 10 by 10 grid. And even if the call stack gets to 100 levels deep, that shouldn't overflow it. So let's talk about what's, where is my part one? Okay, part one. That's part two. There's part one. Okay, so part one, we're just parsing the grid, and then I've got this cycle grid mini. So cycle grid mini says, for count and range, we're gonna do cycle grid. So we're gonna count how many flashes happen, and we're gonna return total flashes. So now, cycle grid, we make a set of our flash locations. So for each day, we clear out which ones have flashed. So for each new day, we're gonna take a new count. Increment grid. So all we're doing here in increment grid is we're just gonna go through and we're gonna add 1 to all the things in the grid. I realized later that we could possibly skip this step, but it's fine. And then we just walk through all of the coordinates, try to flash, and then for everywhere that flashed, we have to set it to 0 at the very end. So if it flashes, it's got to get reset back to 0. And then we return how many flash locations were there, how many locations in the grid had a flash. And then for part 2, we have this function try-synchronize. So day equals 1 while not try-synchronize. So try-synchronize does this cycle grid thing that we just looked at. And then we ask, did they all flash? And we know that they all flashed if all of them are 0. So we're just looping through all the spots in the grid and seeing if any of them are greater than 0. If they are, return false. Otherwise, return true. So we just do a while loop here and see, okay, is everything 0? No? Okay, keep going. So that was pretty straightforward for part 2. All right, we are at 12:57 p.m. and day 12, I want to talk just a little bit about it. As a matter of fact, let's just look at the description for day 12, and then we'll finish up with day 12 next week. So this is a fun problem to solve with a computer, because it's all about building a graph. And this is a special kind of graph in that it's not a directed graph. So what does that mean? That means that A to B and B to A are both valid directions to go. So you're not constrained that you can only go from A to B or from B to A. You can go either direction. So I'll give you a little bit of a hint at this, and then we'll talk about it more next week. One of the things that you really need to make sure that you do is make sure that you've got both directions. So if you're making a map from, say, what are all of the locations from a particular cave to another cave, make sure that you do both directions. So so if you're parsing an entry, so you've got an entry, so like A to B, make sure you've got that mapping from A to B as well as B back to A. So anyway, that's about all we've got time for. Do we have anything on the Twitch stream yet?
Eric just said his part 2 solution on this one took 15 minutes to give an answer, so he still has some more learning to do.
That is some tenacity right there. I would have given up after about 30 seconds. That also shows a lot of faith in your algorithm is correct too, because if you're going to wait around for 15 minutes, I know I wouldn't wait around for 15 minutes unless I was pretty confident this is the right answer.
He said that he went for coffee, nice. And that all the tests had passed.
Hey, if all the tests pass, that means it's right. Maybe. Who wrote those tests? All right, cool. Well, that's all we've got time for. Hopefully you learned something. Hopefully this was fun to watch. Hopefully this was helpful to you. Looking to see you again next week. So next week is our date is the 23rd. Is that correct? All right, so we'll see you on the 23rd, and we're going to start at day 12, and we're just going to kind of see how far we go. I'm proud of us. We got all the way through from day 6 through day 11. So that's kind of our pace. We're getting through about 5 each week, so that probably means we're not going to get all the way through. And that also takes a little bit of pressure off of me, because that, like, days 22, 23, 24, that's when crap started getting hard last year. So maybe I won't have to solve all of them for the sake of being able to explain them on stream. So see you next week. Thanks so much for tuning in.